So, what if I told you that the single most common way we measure similarity in AI is fundamentally broken? It sounds crazy, right? But a pretty startling paper from some Netflix researchers suggests that for a lot of us, our similarity scores might be completely, totally meaningless. Let's dive in and break down what they found.
I want you to just take a second and think about your own work. If you're building a search engine, a recommender system, or really any feature that relies on embeddings, you are using a similarity metric. But what if that metric, the very foundation of your system, could be manipulated to produce pretty much any result you wanted? Yeah, that's the question we're tackling today.
Cosine similarity is just everywhere. It's the bread and butter for finding similar words, products, you name it. It's simple, it's intuitive, and most of the time we just assume it works. But the researchers at Netflix, they've basically uncovered this hidden mathematical trap that many of us might be falling right into. And it's one that could make our similarity scores completely worthless.
And this brings us right to the core of the issue, something they've dubbed the arbitrary similarity problem. Now, this isn't just some small bug in the code. No, it's a fundamental vulnerability in how certain models are trained.
And that right there, that's a direct quote from the paper. It's a really bold claim. They are saying, point blank, that for some very, very common model types, the similarity scores you're getting aren't just a little bit off. They could be completely random.
So you're probably wondering, how is this even possible? Well, the research points a finger directly at the cause. Some training methods create what they call a hidden degree of freedom inside the learned embeddings. You can think of it like finding some extra, unexpected wiggle room in the math that you didn't know was there.
And here is the really sneaky part. This wiggle room, it doesn't actually hurt the model's main job, making predictions or recommendations. Your accuracy metrics can look perfect. But under the hood, that exact same perfectly valid model could be spitting out cosine similarity scores that are just all over the place. The predictions are fine, but the similarities are, well, a mess.
Okay, so where is this wiggle room coming from? The researchers actually traced it back to a choice that many of us make during training without even thinking twice about it: the specific type of regularization we use.
So this slide here really lays out the two paths you can take. Over on the left, we've got a super common objective that regularizes the product of the embedding matrices. The paper proves this is the one that's vulnerable. But on the right, if you regularize each matrix separately, you get a stable, unique solution where similarity is actually well-defined. It's wild to think that the choice between a plus and a multiply in your regularization could have such a massive, massive impact down the line. The paper gets into this concept we can call the arbitrary rescaling matrix, or just D. And honestly, the best way to picture this is as a set of hidden dials on your model. Because of the math in that first regularization method, you can basically turn these dials, which rescales the hidden dimensions of your embeddings, and it won't change your model's final output or accuracy one bit. But, and this is the whole point, every tiny turn of those dials completely warps the geometry of your embedding space, and as a result, throws your cosine similarities into chaos. Now, all this theory is one thing, but seeing is believing. The researchers put together a simulation to show just how crazy this effect can be in the real world. And this just brilliantly illustrates the problem. Look at the far left. That's the ground truth. 5 nice, distinct clusters of items. Okay, now look at the next 3 plots. They are all from the exact same model, trained with that vulnerable regularization. The only difference is how those hidden dials are set. And check out the one in the middle, B equals VK. It creates this totally bizarre but mathematically valid result where every single item is only similar to itself and nothing else. Same model, same data, completely different views of reality. And it is so crucial to get this. We're not talking about a bug in the code or some kind of training error. Nope. This is an inherent mathematical property of using that product-style regularization. And that's exactly what makes it so dangerous, because everything on the surface, all your metrics, they might look perfectly fine. Okay, so the problem is clear, and yeah, it's a little scary, but the good news is the paper doesn't just leave us hanging. It provides some really clear practical fixes and alternatives for any of us who might be running into this. So first up, if you actually care about cosine similarity, then train for it directly. Use things like layer normalization to make it the direct objective. Second, you can just sidestep the problem entirely by not calculating similarity in that latent embedding space. Instead, project back to the original feature space and calculate your similarities there.
And third, you gotta address biases like item popularity before or during training, not just with some quick normalization step at the end.
So, how do you actually put this research into practice tomorrow? Well, you can start by asking these questions with your team or, hey, even in your next job interview. Which regularization method are we actually using? Have we checked if our dot product and cosine similarity rankings even line up? Have we actually validated that these similarities make any real-world sense? Think of this as your new checklist.
But of course, there's a big question still hanging in the air. All of this was proven with linear models. So what does it mean for all the complex deep learning models we're all using today? Well, the paper addresses that directly. So the researchers used linear models for a really good reason. It lets them create a clean, undeniable mathematical proof. But they argue this problem isn't just limited to linear models. In fact, it's probably even worse and way more hidden inside complex deep learning architectures.
And here's their conclusion on it. With deep models, you've got all these different regularizers like weight decay and dropout mixing together across different layers. Each one of them is implicitly messing with the scaling of the embeddings, which just makes the final effect on cosine similarity even harder to see and way, way harder to debug.
Ultimately, this paper is just a really powerful reminder to question the tools that we all take for granted, like cosine similarity. And it really leaves us with a critical question to take back to our own work. What other industry standard practices are we just using blindly? And what kind of hidden flaws might they be hiding from us?